Hey guys, welcome back to another edition in geometry. It's Mr. Anderson here with you, and we're in chapter 5 today. What we're going to do is we're going to combine 5.1 and 5.2 and talk about some different things all together, and we're going to just kind of go past a few things a little quickly. But today we're going to do 5.1 and 5.2, so hang on, here we go. Our objectives today, first of all, we're going to identify and use perpendicular bisectors and triangles, perpendicular bisectors. Number 2, we're going to identify and use angle bisectors. Number 3, identify and use medians, and then identify and use altitudes in triangles. Okay, so all this is dealing with triangles, different types of things there. Okay, let's start with the perpendicular bisector. All right, here's an example of the perpendicular bisector. You can see a little drawing over here. And if you look at the word, and we've talked about both of these words before, perpendicular means what? 90 degrees, right? They cross like this, which makes a 90-degree angle. And if you remember, bisector means it cuts things in two equal parts. So as we just said there, so that means a perpendicular bisector. The bisector itself is this line right here. So that's the bisector. Okay, so this blue line here is the bisector. So it makes a 90-degree angle, you can see right here. And it bisects a side, one of the sides, into two equal parts. And so if you notice here, this is marked as being the same as this. So this line made a 90-degree angle right here, and it cut this side XY into two equal parts. We'll talk about this a little bit more as we go, but this bisector could go on any side. So if it went on, this other side here, it'd make a 90-degree angle, and it would go through here, cut XZ into two equal parts, and make 90 degrees there. So you can have multiple different perpendicular bisectors. All right, example. All right, so let's find the value of X and Y if DE, so here's DE, D is that line right there, it's a perpendicular bisector of ABC. So this is a perpendicular bisector. So what we just said was if this is a perpendicular bisector, number one, it's got to be perpendicular, which means that's 90 degrees. And number two, that it cuts this side over here into two equal parts. So this is equal to that. Okay, so that's what we know. Let's see if we can't find X and Y. Well, first of all, I'm going to start with X, and I say, hey, X here, 5X plus 20 is referring to this angle right here, and we said this is 90. Well, this also has to be 90, right? Because two 90s will make a straight line, which makes 180. So we know, first of all, that we have to do 5X plus 20 will equal 90. Okay, that's our first equation that we're going to write. Minus 20. 5x equals 70, and divide by 5. And so let's see what that is there. 70 divided by 5 is 14. So we have x is 14. Okay, and again, that was because this has to be 90 degrees, so we know that that would have to equal it. What else do we have? Well, to find y, you notice we've got some lengths down here, and we had to mark these as being congruent to each other because of the bisector. So we know our other equation for the y's here will be that 7y minus 6 will equal 4y plus 18. These two have to equal each other, okay? So then we just solve that. Oops, sorry. I was thinking ahead there. Minus 4y plus 6. So 3y equals 24, and divide by 3. And so y equals 8. Okay? So if you have a perpendicular bisector, then you know it makes 90 degrees and two equal parts there, and you can use that to help solve. Okay, now there is a little bit extra. I'm not going to spend a lot of time on this as well, but I don't know why I keep making these stupid marks here. My pen's not even touching the thing. I don't want to spend a lot of time on these, but here's a specific perpendicular bisector If you notice, here's the bisector is CD, makes 90 degrees, and makes these two the same. But in this triangle, the vertex, the C is the vertex, is right on the perpendicular bisector, whereas the last example I gave you, it wasn't like that. But in this one particular instance, then you also know that these two sides here, AC will equal CB. Okay, and as a matter of fact, if you remember in one of the last sections we did, remember side, angle, side, 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 angle, angle, side, those theorems? Well, if you look at this, if this happens here, you notice they share these. You think about, instead of one big triangle, think about two little triangles here. They share this side. They both have a 90-degree angle, and these two are the same. So that means what? Side, angle, side. Huh. That means these two little triangles are congruent, which means side AC is congruent to CB. Isn't that interesting? Okay, so let's just take a quick look at that. I don't want to spend a lot of time on this, but if you notice here, here's what you've got, 90 degrees, two equal parts. So this is a perpendicular bisector. It goes through the vertex up here, so these two need to be equal. So our equation there will be 3x plus 1 equals 5x minus 3. Minus 3x plus 3. So that gives me 2x equals 4. Divide by 2. X equals 2. All right, now we got x equals 2, but the question was find PQ. So PQ here is 3x plus 1. So PQ would be 3 times 2 plus 1, which is 6 plus 1, or 7. And if you want to check yourself, since these two have to be the same, you could plug 2 in here as well. And if you do that, 5 times 2 is 10. 10 minus 3 is 7. All right, cool. All right, and again, this is another thing. I want to just mention it to you, but I'm not even going to do a problem on this, but just to get you familiar with this, you know, to have heard this word before. When we're talking about perpendicular bisectors, if you take, remember I said before, you can have a perpendicular bisector that comes from every side. Where all three of those perpendicular bisectors meet would be like right here, this point P right here. That's called the point of concurrency, where all the points come together. When they're talking about perpendicular bisectors, that point where they come together is called the circumcenter. The cool thing about the circumcenter is that when you take those perpendicular bisectors, which is in red, that point is the same distance, which these are the lines in blue, from P to A, from P to C, and from P to B. Those are all equal. And so if that comes up, I'm not going to do an example today because I don't want to focus on that, but you could make those two things equal to solve an equation, okay? All right, next, angle bisector. Okay, here's an example of what would be an angle bisector, and an angle bisector would split an angle in two equal parts. And so you can see it bisects an angle into two equal parts, and so that means this angle would equal this angle. So these two angles would equal each other. Okay, so that's the main thing to remember about an angle bisector. So let's do an example with that. Here's an example. We've got a triangle, and it tells us it's an angle bisector. So we know that this red line, again, this red line, that's our angle bisector. And so it means this angle is congruent to that angle. And we have these marked here. And so we say, oh, well, if these two angles have to be congruent, my equation would be what? 3x minus 6 equals x plus 20. And then I just solve that, so minus x plus 6, 2x equals 26, divide by 2, and x is 13. Okay, so we found x, but we also said find the measure of angle DBC. Well, DBC, which one is that? D to B to C, so it's this angle here, which they should be the same anyway, right? And so we'll just plug it in there. So that's going to be the measure of angle DBC equals 3 times 13 minus 6. 3 times 13 is 39. Minus 6 is 33. So 33 degrees. And if you take that 13 and plugged it into x plus 20, what do you get? 13 plus 20 is 33. Same thing. Excellent. So you can check yourself that way. All right. Another thing here, I just want to briefly look at this, but I don't want to spend a lot of time on this either. This angle bisector theorem just says if you have an angle, and then you've got an angle bisector that goes through that, any point on that bisector is the same distance. If you go 90 degrees from each side, it'll be the same distance. So in this case here, if you notice, you take that point F, from D to F is the same distance as F to E. And again, it really goes back to that same concept of two smaller triangles, and side angle side, side, and that kind of stuff to show that these two smaller ones are congruent. And so therefore, these sides are the same, the angles are the same, so forth. Okay, so quick look at one of those. So again, what I just said there was what we've got a angle bisector. These two angles are the same. And in this case, technically what it comes down to is they share these. If you think about two smaller triangles, they share this side right here. And what do you have? 90 degrees angle that's same as this one, and then a side. This is angle, side, makes these two congruent to each other. So therefore, every matching side and every matching angle has to be equal to each other. So in this case, we would just do 4x minus 1 equals 3x plus 2, because these have to be the same in this situation. So minus 3x plus 1. And it looks like we have x is 3, but we're trying to find qs. So qs is what? 4x minus 1. So qs equals 4 times 3 minus 1, which is 12 minus 1, or 11. And what should happen is if you plug that in, plug it in here, 3 times 3 is 9. 9 plus 2 is 11. All right. And again, here's kind of going along with the one we looked at before. The incenter is when you take all the angle bisectors and see where they come together. Okay, so in this case, now they did these both in blue. It makes it a little hard here, but remember the angle bisectors is the line coming from A to P, B to P, and C to P, where all three of those angle bisectors come together. And the thing that's kind of cool about the incenter is that from that point, it's the same distance from that point perpendicular to each side. So from P to E, from D to P, and P to F, those are all congruent, where it's got the little darker blue line here. Okay, again, I'm not going to major on that. I just want to, show you the name, get you familiar with what's happening there, but we're not going to put a lot of work into that. Okay, the third thing today is median, the median. And if you notice, here's the median. Remember, median kind of means like the middle, right? And so we've talked about, I think about this before, the median basically splits a side into two equal parts. And so it's also basically, it's kind of, in a sense, it's a bisector, right? It bisects this side, but we call it the median. And so here's how we would use that. Find the value of x in AC. So here we say this is the median. Okay, so again, this line here, that's the median. And so what it does is this splits this side into two equal parts. So this is equal to that. So if you haven't already figured it out, our equation is 3x plus 8 equals 2x plus 17. So we subtract 2x, subtract 8. So we have x equals, looks like 9, right? So that's one thing that we want to find. And then we also want to find AC. Oh, now this is interesting. So AC is what? That's the whole length. So what we can do is if we wanted to, we could add these two together and then plug it in once, or plug it into each of these, or plug it into one or the other and then just double it, assuming that we're correct. Let's, just to make sure, to double check ourselves, let's plug it into each of these. If I plug 9 in here, that's 3 times 9 plus 8. 9 times 3 is 27, plus 8 is 35. And over here, 2 times 9 plus 17. 2 times 9 is 18. 18 plus 17 is 35. That's good because it shows us that these are both the same. So we kind of checked our work. And so that means altogether AC is 70. 35 plus 35. Okay, good. The centroid theorem. I know it sounds like a cartoon character, the centroid. This is when you take the median from each side, and this is the point where they all come together. The key thing about this one is it's 2/3 the distance from the vertex to the midpoint of the other side. So like, for example, when you take this median from B to P, that's 2/3 the distance, and then from P to L is 1/3 of the distance. You know, from A to P is 2/3 of the distance, and then from P to K is 1/3. So again, knowing that, you could solve some problems. We're not going to go into that today, but just know that there is this thing called the centroid, and you know, if you can remember the 2/3, 1/3 thing, great. If not, you'll see it later. All right, last thing. The last of those four things we want to talk about is the altitude. Okay, so the altitude, if you notice, here's a diagram with the altitude marked, and you notice it makes a 90-degree angle. And so that's kind of the big thing there, is that it makes a 90-degree angle, which was the same as the perpendicular bisector. But you notice here, the other thing is, obviously, according to this diagram, these two are not equal sections over here. So this is not a perpendicular bisector. What makes it different is that it goes to the vertex of the opposite side. So it's 90 degrees, but it goes to the vertex. So it's not in the middle of this side, but it's whatever it takes to get to the vertex. But the key thing to remember there is the 90 degrees. Now, the other thing is, with altitude, what could happen is the altitude could be inside, like this one is how we normally think of it, interior, but it could also be exterior or right on the side of a triangle. So it could look like this. Notice the red triangle here, and notice here the altitude has to go to the vertex, so straight down at 90 degrees puts the altitude outside of that triangle, so it has to be out here. Okay, it's not inside in this case. And then, of course, if you have a right triangle, you notice here the black is the triangle, and this red line is the altitude, which is right on the side of the triangle. It has to go from the vertex straight down 90 degrees. So you could have several different variations there on the altitude. All right, let's look at an example. This is like kind of the standard kind here where the altitude's inside. And remember, the whole thing on this one is what? That the altitude makes 90 degrees. So you know that has to be 90 degrees. Which is what this, and this angle over here is also has to be 90 degrees, right? So that means 5x plus 15 has to equal 90. Kind of like what we did with the perpendicular bisector before, same thing. And so we just subtract 15. 5x equals, what, 75? And then divide by 5. And that would give me 15. Okay, 15. All right. And of course, as with all the other things that we looked at, there's a special thing here called the orthocenter. In this case, it's where all the altitudes come together in the middle here. And basically, there's really nothing awesome or special about that point. Like, you know, the other ones where it's the same distance or 2/3 and 1/3. This is just, it's a point, and it's called the orthocenter. So, so not much that we can do with that one. All right, so lastly, to wrap this all up, here's the overview of all that we talked about before. So we had four things: the perpendicular bisector, which meant what? A 90-degree angle, two equal parts. The angle bisector, which means you have two equal angles. The median, which means you have two equal sides. And the altitude, which means you have 90 degrees. So that's the main thing that we're going to key on are those things. But then also remember that the circumcenter goes with the perpendicular bisector, and in that case, that point of the perpendicular bisectors, it's from that point to each vertex is the same. The incenter goes with the angle bisector, and so when you do the angle bisectors, that from that point where they come together to each side is congruent. The centroid is where the medians all come together in the middle, and if you remember, at that point on each median, 2/3 of it is from the vertex to that point, and then 1/3 is from the point to the side. And then the orthocenter is just, it goes along with the altitude, and there's nothing special in there to deal with. Okay, so that's it. Dealing with bisectors, medians, and altitudes. Kind of sounds like that could be a law firm or something, you know. Welcome to bisector, median, and altitude. Well, anyway, that's it. This is Mr. Anderson. We'll talk to you next time. Bye.